what we're going to do in this experiment is measure the index of refraction of this semicircular prism. Now, in your optics kit, you should have received the semicircular prism, a rectangular prism, um, and a few lenses, well, two lenses, and then a third prism that is triangular in shape. Okay? And all of these substances are going to be made out of the same material, so they should all have the same refractive index. Okay? And so the easiest method, if you have a semicircular disc, this is the easiest object with which to measure the index of refraction experimentally, due to the fact that the semicircle nature means that the laser light, when the laser hits the boundary here, it will refract, but when it hits the boundary here on the semicircular edge, it will not change direction. It technically is refracted, but it will not change the direction of the laser beam, due to the fact that effectively over short, small distances, every exiting point on the semicircle is normal to that surface. So what that means is that if you have a protractor, okay, what that means if you have a protractor, and the protractor I'm using here is going to be available on Blackboard to download and print off. And so the way I have this arranged, the 0 degree is up here, and the 180 degree is down here, and the flat surface of the prism traverses the 90 degree and 270 degree line. Okay, now, so what you want to do is you want to make sure that this is as straight as possible. Okay, as straight as possible. But one way to make sure that everything is set up properly is to let your beam, now notice, before I get into that, actually notice the current experimental setup. All right, so you want to build your setup, and you can use books or magazines, stacks of paper, whatever you may have around, but you want to set this up such that however your laser is built, that what I've done, okay, by the way, is I've taken like a little piece of paper towel and wadded it up and then taped it down to hold the power button down, right? So you may want to get clever with how you keep your power button on. But depending on your build, it may be as simple as just wrapping a piece of tape around it. The buttons on these types of laser pointers are indented, so just putting a piece of tape around it wouldn't do anything. But then you want to adjust the height of your laser to just graze the protractor. And if you just graze the protractor, you can see the beam run across the front of the paper, and then you can see the beam on the back end as it exits the prism. And it may be a little hard to see in the video, but it is there. All right, it is there. And I'll post some pictures as well. And you can tell that your setup is operating appropriately when, if the incoming laser is directly along the line that correlates with it with 180 degrees, then when it hits the prism, it should exit at 0. Okay, and you should be able to see the path of the laser along the entire back sheet of paper. Now, it might change in intensity. It's a little brighter back here than it is on the protractor, but you should be able to see it. Now, you want to do this in a darkish room. You don't have to have it completely dark, but you'd want it to be in somewhat of a darkish environment. And in fact, let me actually close my shades a little bit more. See if that helps anything. And so now what we want to do, all right, is we want to move the laser pointer around and we want to go every 5 degrees. So you want to maneuver your laser so that it's on the 5-degree mark and it's headed straight down the line. Okay, you want your laser pointer to be straight along the radial direction of the protractor, and then you can read off where the measurement is on the other side. And we want to do this every 5 degrees. So now I'm at 10 degrees. Right, that's pretty close. And you'll notice, okay, and by the way, when I say I'm at 10 degrees, I started at 180 and I'm now at 190, so I've shifted 10 degrees. Over here on this side of the protractor, it'll just read the actual degree increments. You don't have to do any subtraction or anything. But you'll note, okay, so I've shifted the laser beam 10 degrees over on this side, and the 10-degree mark is right here, and the laser beam is in front of it. So the outcoming beam has not shifted by a full 10 degrees. It has shifted, in this case, by about 6. Now remember what we're verifying here. Snell's law says that the index of refraction before it enters the medium, multiplied by the sine of the angle that it makes with respect to the normal. Now in this case, the normal is 180 degrees. That line is going to equal the index of refraction in the object multiplied by the sine of the angle coming out. But because the beam is not deflected back here, because the prism is normal at every point where the beam leaves here, then, and by the way, that works because there's one more thing you want to do, and I forgot to specify this, and that is you want the prism to be as centered as possible. So you want the prism to be as centered as possible. It will work if you offset it. So like if I do this kind of thing, it will adjust things slightly. So you do want to have it as centered as possible. But when you do, okay, and you get things set, then, and you want to disturb the system as little as possible, right? You want to disturb your system as little as possible. But in any case, so then you take that measurement, and then we can go to 15 degrees and take another measurement. Oh, and what I was saying, so the sine of this angle should be larger than the sine of this angle because the index of refraction of the prism is more than the index of refraction of air. So to keep that equation constant, n1 sine theta 1 equals n2 sine theta 2. If n2 is larger than n1, then theta 2 should be smaller than theta 1, right? So you want to then take measurements every 5 degrees, okay? Every 5 degrees, take a measurement for a total of 40 degrees, okay? So you're going to have 8 data points. And if you do that, if you get 8 data points, what you can then do is plot the index of refraction. Well, okay, so what you want to do is plot the sine of the angles against each other, okay? Because we're wanting n2, all right, n2 is going to equal n1 sine theta 1 over sine theta 2, okay? Actually, I lied. That's a true statement, but what we're wanting to do is measure n2, okay? So what you want to do is plot sine theta 1 against sine theta 2. So you want to put sine theta 1 on your y-axis and sine theta 2 on your x-axis. And what that will do is, because n1 is air and it's 1, it's effectively 1, n1 goes out of the equation, right? n1 goes out of the equation, and so you've got sine theta 1 equals n2 sine theta 2. So if you use sine of theta 2 as your independent variable and sine theta 1 as your dependent variable, then you get an equation y equals mx, and the slope would be the index of refraction. So plot your sine of your angles on your n1 side on the y-axis and the sine of your angles on the other side on the x-axis, your sine theta 2's on the x-axis, and you should get a linear line. And the slope of that linear line should be the index of refraction of your piece here. Okay? All right. That is lab number 7.